The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Welcome to for the speaker feedback. Welcome to QLab's webinar on the essentials of laboratory weathering. We are coming to you live from Cleveland, Ohio. On a not nice weather day. It's a little bit wet and rainy and cold, but we're excited that you're here. Thank you very much for joining us in today. Some housekeeping things before we hand it over to Bill and we talk about laboratory weathering. We will be distributing the slides of this presentation probably tomorrow, as well as a recording of this presentation, so you could watch it again or share it. Watch your email for that. We'll send it to everyone that attends the webinar today. If you have a question during the webinar, you can use GoToWebinar's question feature. Submit your question. We have some folks here that will be answering them during the webinar, and then we'll have time at the end too for questions. So you may get an answer during the show, but if the question is really good and really relevant, we'll answer it for everyone so everyone can see the answer or hear the answer. So without further ado, let me hand it over to Bill Tobin and today's webinar.
Thanks, Mike. As Mike introduced me, my name is Bill Tobin. I'm a Senior Corrosion and Weathering Technical Marketing Specialist for QLab. Today we're going to be talking about the essentials of laboratory weathering, but before we get into that, I want to let you guys know a little bit more about QLab. QLab was founded in 1956, where we started manufacturing standard test substrates for paints. We still manufacture those today, but since then we now specialize in material durability testing equipment and also testing services. So our primary manufacturing location and headquarters is located in Westlake, Ohio, just outside of Cleveland. We also have offices in Bolton, England, Shanghai, China, and Saarbrücken, Germany. Additionally, we have a number of outdoor and accelerated test labs. So our outdoor weathering sites are located in Miami, Florida, Phoenix, Arizona, and here in Westlake, Ohio. We also perform accelerated weathering testing at our Miami, Florida location and our German office. Now, you might be asking, why do we have sites at Miami and Phoenix? We'll talk about that as we get further into the presentation. You'll understand the importance of those sites when it comes to outdoor testing. But before we can really talk about laboratory weathering, we have to understand the basics of weathering. So that's what we're going to get into here first. So when we say weathering, what we're referring to are changes in material properties resulting from exposure to radiant energy present in sunlight in combination with heat and water in its various states. So really the key here, the key takeaway is when we talk about weathering, we're talking about sunlight, heat, and water, all three factors together. There are some other factors that impact natural weathering in particular, such as pollution or bacterial growth, but we're not going to really cover those today because we're going to focus on the key three features that are used in laboratory weathering, which are sunlight, heat, and moisture. So the first factor of weathering that we're going to talk about is sunlight. This is the one that's usually considered like the major component when we talk about weathering, because usually when we're doing weathering testing, we're interested in the effects of photodegradation on materials. So what is sunlight? Sunlight is energy that we receive from the sun, hence its name. We can express this as a form of electromagnetic radiation, and that radiation can be further expressed in terms of irradiance, which is the intensity of that energy, and wavelength, which has to do with the size of the photons and the frequency of those photons hitting a surface or a material. So when we're talking about sunlight, the area that we're primarily focused on is between 295 nanometer wavelength and 3000 nanometer wavelength. Those particular numbers are not necessarily important, but the key thing to take away is that there are three components of sunlight. One is ultraviolet energy, one is visible energy, and one is infrared energy. Visible is, as you'd expect, that's any light that you can see that forms the color spectrum. Infrared is not visible, but it does cause heating effects. And ultraviolet isn't visible, causes a minor amount of heating, but more importantly, it is the major effect in photodegradation of materials. So even though it's only a small portion of the sunlight that we receive, almost all polymer degradation can be caused by UV. That's kind of why we're going to focus largely on the UV portion when we look at the different effects of sunlight. And again, when we start getting into laboratory weathering apparatus, you'll see that we still focus on the UV portion of the band. So we're going to show some charts here, but I think it's important to get some terminology out of the way. The first one is irradiance. We're going to use that a lot. That is kind of the rate at which light falls on a surface. That's the intensity. That's what we're going to be talking about. There's also radiant exposure, which is intensity over time. Some testing is done to that, but I don't think it's necessary for discussion in this presentation. And then finally, spectral irradiance, which is the irradiance for a particular wavelength. That's really what we're going to be focused on. As mentioned in previous slides, UV is what we're looking at, and particularly shortwave UV. So we're going to focus on the spectral irradiance in that range. So what we have here is we have a chart that shows a couple of standards that determine a lot of the weathering testing information that we use in regards to light. Both CIE 85 and ASTM G177 are standards that express the noon summer sunlight spectral irradiance of that. And so what we're really focused on for noon summer sunlight is this is the worst case experience that a material will see outdoors. When we talk about accelerated testing, we don't necessarily want to subject things to unrealistic conditions. We just want to subject them to realistic conditions and the maximum of that for longer periods of time than they would see outdoors. So outdoors, you'll only see noon summer sunlight probably a total of maybe 3-4 hours over the course of a year, whereas in a lot of weathering tests, we're going to try and simulate this continuously. And you can see here in this chart how low the UV is relative to the visible energy. We didn't show the infrared energy because it goes out pretty far, but the visible is the largest portion of this. And you can see the UVA is much smaller and the UVB range even still. We have a little arrow here that points out the UVC range. We point that out because some tests for other applications will use UVC energy. We don't use it because it's not realistic towards to what's actually seen by materials outdoors. There are things that can modify the spectrum. The reason we say noon summer sunlight is that the time of year has a large impact on it. The highest intensity of sunlight that we see is where the smallest amount of atmosphere is between the sun and the surface of the earth. So as you're looking towards wintertime, the energy has to travel through more atmosphere, and so it's filtered further, and we see lower amounts of energy. Time of day, same effect. As the sun is setting, it has to cut through more of the atmosphere, and that's why it gets that red hue. And also latitude. Latitude has more of an effect on the spectrum that you see during the winter. In pretty much all locations, you're going to see very similar spectrum in noon summer sunlight. But the difference is that in Florida and Arizona, you're going to see a lot higher spectrum than you would during the winter months than you would in, say, London, Berlin, or anywhere in Canada. So that's why those are used as benchmark sites. We also have a note here to talk about altitude. Most of the filtering happens in the upper stratosphere, so generally speaking, altitude isn't a major impact. The only time that you might be concerned about that is if you're designing materials for flight. If anything's flying up at high altitude, you may need to use a different spectrum. Another effect on spectrum has to do with window glass. What we showed was an outdoor exposure, but a lot of materials that experience weathering aren't actually installed outdoors. They could be in a vehicle or in a storefront. And so it's important for us to characterize what sunlight through window glass looks like as well. As you can see, not only is the energy decreased, but the shortest wavelength, or what we call the cut-on wavelength, goes from about 295 nanometers to about 310 nanometers. And that actually has a huge impact on the degradation of materials, because some materials may only be sensitive to energies between 295 and 310, which means that they'll see degradation outdoors, but they won't see any degradation indoors. This is also just for a standard 3 millimeter thick clear glass. There are changes to that spectrum based on the thickness of the glass and what kind of tinting is on the glass, or laminates are on the glass. So as you can see, the actual spectrum that materials experience inside a car or in a storefront are going to be really dependent on the thickness of the glass and any kind of tinting. So the reason we go through all this is it's important to identify what the actual end-use environment is for your material when you're trying to figure out what accelerated lab test you're going to use. So know the application, and then we can figure out the best way to simulate that sunlight. The next factor of weathering that we're going to talk about is heat. Now, apart from the fact that any kind of elevated temperature increases the amount of reactions in solution, there are a number of effects that heat can have, particularly when we talk about thermal cycling. A lot of these materials are coatings on substrates, and if the substrate and the coating have different expansion and contraction properties, heating and cooling, fast heating and cooling in particular, can cause stresses between those materials. So dimensional change and thermal cycling are very important to simulate in weathering. Additionally, for materials that have solvents in them or anything like that would hold them together and keep their durability, evaporation is another important effect of heat. This is just one example of a test that was performed using different temperatures, and this was performed in a fluorescent UV test device, the QUV. The irradiance was exactly the same between these three tests. The only thing that varied was the temperature, and as you can see, at 50 degrees C, the oxygen uptake was much higher than the tests at 30 or 10 degrees C. So this is an example of temperature accelerating the effects of photodegradation and oxidation. To give, again, going back to realistic scenarios, thermal cycling is a real problem, particularly in Florida. If you're in the middle of the summer, hot day, and you have, say, like a dark colored material, those can get very hot. It's not unusual for those materials to get up to 75 degrees Celsius. And almost every day in Florida, that might be an exaggeration. It seems like every day here in Cleveland, they'll get a short rainstorm, and in the course of 2 minutes, that material that was 75 degrees Celsius can drop to 25 degrees Celsius, and that causes a lot of stress, particularly on anything that's got plastics in it, because plastics have greater expansion and contraction. Another thing to keep in mind about temperature is, as we mentioned, I mentioned dark colored materials. The color of a specimen outdoors has a huge impact on what kind of end-use temperature it's going to see. In particular, what this study identified is that materials outdoors could be as much as 25 degrees C hotter when you're comparing a black specimen to a white specimen. This also shows the difference between the installation mechanism for these, because the chart on the right shows plywood-backed specimens. So that means that they're insulated and they don't have a lot of cooling on the back, whereas on the left there's cooling on the back of metal panels. So these are all things to keep in mind as far as characterizing the end-use environment for your material, because we're going to want to simulate this in our accelerated test as best as we can. And then the final thing that we want to talk about in regards to heat, particularly for automotive interiors, but this also applies to any kind of testing for roofing or anything that's going to be in an attic space, that the temperatures in these areas can often get very high. Anywhere where the heat can be trapped can get very high. Automotive tests, it's not unusual for some of the temperatures to exceed 100 degrees Celsius, and so again, know the application, and then you can design an accelerated test around that. The third and final factor of weathering that we're going to talk about is water. And this is probably the one that is the most difficult to simulate for accelerated laboratory testing, and probably the one that's least understood as far as the importance for long-term durability of materials. Water has a lot of major effects. Primary ones that we see a lot are erosion and thermal shock that we talked about, impact that peels material off the front layer of say a coating or a plastic can be important. But water also has a lot of effects on chemical reactions, as far as like facilitating those reactions in solution, and also water is probably the number one way for oxygen uptake and oxidation of materials. So water is really important for us to understand. And one thing to note is there was a standard that was developed recently, and so the reason the standard was needed is for automotive coatings. They found that over the course of between the 70s and the 80s, they made automotive coatings very, very durable in regards to ultraviolet. So they can keep color and they can keep gloss. And that's why you rarely run into like the fading that you used to see in vehicles. But now almost all the failures of paints that you see are blistering, cracking, crazing, and these are all artifacts of water. And these are harder to test because the tests that they were using were very good at simulating the UV, but not as good at simulating the effects of water. So let's talk about the three ways that we characterize water. The first one is humidity. So this is an important one, particularly for anything that's going to be behind window glass or an automotive interior, because it's water in the air, and all materials are going to be subject to humidity. And that can lead to physical stress on a lot of materials. And so the best way for us to characterize that is we use the term relative humidity. Relative humidity represents the amount of water that can be held in the air at a certain temperature. And so at 100%, that means the air is fully saturated and no additional water can be held, and that's when condensation forms. The next form that we're going to be talking about is rainfall. So rainfall is, the obvious effect that we think about when we think about weathering. It can wash away surface layers. A lot of materials experience chalking or dirt accumulation, and over time those can actually cause resistances to further photodegradation, and rainfall can wash those layers away and continue photodegradation on those materials. And also rainfall is the best way for us to do thermal shock. For fast thermal changes, that's the only way to do it. Sorry, I'm having a small... Sorry about that. I lost my connection to the TV, and it caused a bit of a backup there. So sorry about that. Let's go back here. So now that we talked about rain, we're going to talk about dew. This one's very important for us to talk about because this is actually the most common form of wetness for materials outdoors. This is when moisture from the atmosphere forms on a cool surface, and because it's forming out of the atmosphere, it's very pure and has... All right, hold on one second. I apologize for this. Let's see. All right, can you guys see the slides now?
Yep.
All right, sorry about that. I was showing my second monitor and lost it. So as I was saying, dew, which is condensation that forms when the air around a cool surface is fully saturated, has a large amount of oxygen since it's just forming out of the air, and has a very long dwell time on materials. And in fact, it's important for us to note this because dew, not rain, is the source of most outdoor wetness. You know, we did some studies of time of wetness in various locations throughout North America, and what we found is that apart from situations like the desert in Arizona, whether we were talking about a coastal location or like a subtropical Florida location or a northern temperate or even like a cool northern climate, materials would be wet from between 8 to 12 hours a day, and that was because of dew. So this is something that's hard for us to simulate in accelerated weathering tests, but it's very important for the actual test itself. So this is something that, if there's anything that you take away from this presentation, it's that you shouldn't underestimate the effects of moisture. It really changes the rate of degradation because it facilitates those reactions in solution. It changes the mode of degradation for a lot of materials, and it's very difficult to accelerate. As we always say, it's hard to actually have water sit on a panel faster. So let's bring it all together. So as a summary, sunlight, we're really focused on the UV portion because it causes most polymer degradation. And because of the change in the cut-on, a small change in material formulation or spectrum can have a huge effect on material durability. When we talk about heat, adding heat to sunlight will increase the rate of photodegradation. And also, it's important to know the actual end-use environment because the material's color and mounting can have a strong effect on how hot it gets in an end-use environment. And then finally, moisture should not be underestimated. Adding that together with sunlight and heat is what we call weathering. Dew, as opposed to rainfall, is the source of most outdoor wetness, and products that are outdoors are wet a lot longer than we used to think. So with that information in mind, let's go ahead and start talking about why we actually perform the laboratory weathering. There's lots of different reasons why people might perform laboratory weathering. You might be looking at developing a new material, and maybe that new material needs to be more durable, or maybe you need that new material to have a lower cost. Maybe you have to meet a specific specification to be able to supply a product, or maybe you need to verify that somebody who's supplying you a product is actually meeting the claims that they're making. And then it also helps enhance your reputation. And in the case of some environmental regulations, you can stay ahead of them and develop new formulas that meet the strict environmental requirements while still maintaining the necessary durability for that application. So there's lots of different reasons why you might test. But what's important to note about laboratory testing is that this is not a guaranteed solution for all applications. What it is it is a way for you to make decisions. Do I go with A or do I go with B? Should I make this more durable, less durable, or is it acceptable? It helps you make decisions faster. It helps you reduce the amount of risk associated with those decisions, and it allows you to get to market a lot faster. But it isn't a replacement for natural weathering. So we're going to talk about 4 different types of tests. When we talk about weathering, we think every test program can fall into really 4 different categories. The first category is quality control. This is designed to be a short, easy to run, low-cost test that you can run on every lot of material. And really what you're looking for is catastrophic failure in the formulation of the part. Did somebody forget to add the UV stabilizers? Did somebody, fail to actually seal a part? So this is going to be like a fast test, and this isn't going to give you any correlation to how it's going to perform outdoors. It's something that you can run on every lot that won't break the bank, but will tell you whether or not a supplier has changed the way that they do things. The second one we talk about is a qualification or validation. So this is a kind of the next step up from a quality control test. Once again, we're looking for a pass-fail on a material. But now it's got a little bit more science behind it. A lot of times when these qualifications or standards are developed, they've done a lot of testing, and the person who's giving you this requirement usually knows what they're looking for. So they've done a lot of the footwork in determining that this is a good test. But for you, all you have to do is run the test as specified, or run your material against a reference material and see if your material is better or passes the requirements. Now, the next one that we're going to get into is correlative testing. And you'll notice we have that bold line in between qualification and correlative testing. And that's because everything that's below this bold line, you really need to have natural exposure data in order to be able to perform this test. This is where we get into some of the limitations of accelerated laboratory weathering testing. So correlative testing is kind of R&D research that you're looking for. I have a new formula. I want to see how it performs relative to an existing formula. Maybe it's lower cost. Maybe it's using meets a new regulation. Maybe it's a new color that you're testing, and you need to run this in a test to get some decisions quickly. But the problem is, in order for you to know that you're actually testing correctly, you need to know that your accelerated test gives the same results on known materials as the outdoor test. And in these cases, what we normally look at is rank order. If you have a series of materials, you're really wanting to look for an accelerated laboratory test that gives you the same best performer and worst performer as the outdoor exposure. And this doesn't necessarily have to be at a benchmark site. Testing at benchmark sites is inexpensive and fairly easy, but this could be based on customer claims or customer returns. Because if you have an idea of how it actually performs outdoors and how it fails outdoors, then you can establish correlation to an accelerated test. Now, finally, this is the one that everybody's looking for. It's predictive tests. So once you go past correlative testing, you're looking for an acceleration factor or service life. If something lasts 1,000 hours in a test, does it last 5 years outdoors? And you can come up with this information, but it's important to note that this information requires strenuous weathering testing, lots of data accumulation over years and years, over numbers of different formulas, so you can start to get an idea of what actually changes the durability factors for your materials. There is no one number that's going to solve this problem. There is no magic number that's going to give you an acceleration factor in a QUV or a QSUN. But you can start to establish that data and come up with that information. As a note, it's kind of good that there isn't one number, because if you put in the legwork and you come up with this data, that is a competitive advantage that you have, and your competitors are going to be years and years behind. So while that's the end goal, really we're focusing on correlative testing because that's the easy one to get into today. So I mentioned natural weathering and outdoor weathering, so let's put a definition to this. Natural weathering is an outdoor exposure of materials to unconcentrated sunlight to assess the effects of environmental factors on the various parameters of the material. So what we're looking at is we're putting it in a real-world situation. We want to know how the material actually fails, and in general, we want to use some of the worst case conditions within reason that you can find outdoors. And for that, we have global benchmark sites. And South Florida is a global benchmark for subtropical, which means it's high irradiance, high heat, high moisture. Arizona is a benchmark site for dry desert, which means it's very high irradiance, very high heat, low moisture, and significant temperature shift from day to night. And then Midwest, Northern Industrial is a place where you're going to experience both UV and moisture, but you're also going to have some freezing and some pollution effect on the natural exposure. So why is it important? Well, it would be great if we could come up with a tester that could simulate exact natural weathering every time, but the fact of the matter is natural weathering is very complex and it's variable. Year to year it can differ, and so there is no substitute for actual natural weathering. Accelerated laboratory tests, a lot of the quality control tests that we have, they're not realistic. If we use spectrums that we don't see on the surface of the Earth, we might get fast results, but they're not realistic. And so in order for you to know whether or not an accelerated test is giving you good data, you need to verify that it meets the same failure modes as an outdoor test. And again, we mentioned it, outdoor weathering testing is not expensive, and that data is very, very valuable. The only problem with natural weathering is if you want 2 years of outdoor weathering, it's going to take 2 years. We can't do it any faster. So if you're thinking about starting a weathering program, start outdoors as soon as possible. That's the best thing that you can do. All right. Now that we've talked about why you're performing laboratory weathering and what weathering is, let's talk about the two basic architectures that we have. The first one we're going to talk about is xenon arc. This is a test method where you use a xenon arc lamp, hence the name, and a xenon arc lamp puts out a spectrum similar to sunlight, and the materials are exposed to that light either rotating around the xenon arc lamp or on a flat tray parallel to that lamp, and then they're subjected as well to light and moisture and heat. as for it to be a weathering test. These are some examples of xenon arc lamps. The two primarily used functions for that are air-cooled, which is cooled by blowing lots of air across them, or water-cooled, which are cooled by running very clean distilled deionized water over the surface of them. And on the right is kind of an assembly that shows you where the water passes. There are other effects on the spectrum. We said it's similar to sunlight, but it's similar to sunlight before it hits the atmosphere. So we do have to use optical filters to simulate the effects of, natural daylight, daylight under glass, things like that. And in some cases, we might want something that's a little bit more extreme so we can get faster results, even if it's not realistic. We also have to set the irradiance level, so we have control of the intensity. So we want to dial that in. For an accelerated test, we do want it to be high, but we don't necessarily want it to be unrealistic. And also, we have to pick where we want to control the wavelength, because xenon arc lamps age and their spectrum changes over time. So picking a good wavelength to control it is very important. So as mentioned, here's an example of sunlight outside of the atmosphere and the unfiltered xenon arc lamp. And you can see there's a close match there. But what we're normally testing to is that noon summer sunlight. So we need to apply optical filters to get closer to that black line. So there's three types of optical filters families that are used in xenon arc tests. The first is daylight. These are designed to simulate sunlight through direct exposure. And so, that 295 cut-on that we were looking at, that noon summer sunlight, is really what we're targeting there. The next one is window. These are designed to simulate sunlight through window glass for applications in automotive interiors or storefronts. And then the third one is extended UV, where we add some filtering, but we don't. It's not realistic to daylight cut-on. Again, that is something that you might use for a quality control test or a qualification, but doesn't necessarily have very good correlation. Here's some examples of the daylight filters that QLab offers for their QSun xenon arc tester. And as you can see in that UV range that we're really interested in, particularly in the cut-on, they're all very close. But in the visible range, they stray a little bit. So part of that has to do with which filter you want to pick and how you control the test. For window filters, the black line in this case is standard for sunlight behind window glass. And as you can see, the cut-ons vary a lot more in this case, and that's because there are different types of glass. Are you talking about a 3 mil thick glass, or 5 millimeter, or tinting, lamination? These are all things that you keep in mind. So identifying which window glass is appropriate for your application is important for picking the right filter. And then here are some examples of the extended UV filters, and as you can see, the cut-on is far shorter than the actual cut-on of noon summer sunlight. So again, not realistic, but that might be the test that you're looking for. We mentioned water-cooled and air-cooled. Something important to note is that optical filters in water-cooled architectures will need to be replaced every 400 to 2,000 hours because there are contaminants that deposit on the glass and affect the transmittance over time. For air-cooled systems, you generally do not need to replace them. The only exception to that is the window IR filter, which has an IR-resistant coating that over time solarizes. So that one you need to replace essentially every 8,000 hours. These testers are capable of controlling the irradiance. What they have is a sensor in the chamber that measures at a control point, and that feeds back into the controller, which adjusts the power. So we can maintain control of the irradiance very well. But the important thing is identifying which control point you want to use. There's three options that are primarily used. The first two are narrowband, so it's measurement at a single nanometer wavelength, and that's 340 nanometers, which is primarily used for outdoor exposures, and 420 nanometers, which are used for behind window glass exposures. You also have the option of using total UV, which measures the UV between 300 and 400 nanometers. That gives you kind of a middle ground between 340 and 420. The fourth one that we don't suggest using is global, which is 300 to 800 nanometers. The problem is that as xenon arc lamps age, most of the drop is in the UV range. So if you're controlling in that visible range, you're not going to be getting a similar UV output. And as we mentioned before, UV is the source of almost all degradation, which is why this is not a suggested control point. So as the xenon arc lamps age, generally speaking, the irradiance below the control point will drop slightly, and the irradiance above it will increase slightly. And because of that, lamp life is normally about 1,500 hours for xenon arc testers. But controlling wavelength at your region of interest will maximize repeatability and reproducibility of your test. As far as controlling temperature in these test methods, we use a black panel temperature control. As we mentioned before, with the colored specimens for temperature, the idea is that it approximates a maximum specimen surface temperature. It's not going to be necessarily the hottest point in a chamber because specimen materials will play a large role in that, but this is the common control point that's used in test methods. And this can be used in combination with a chamber air temperature sensor, but it isn't required. There's two types of black panel temperature sensors. The first one is what is called in ASTM an uninsulated black panel, but in other standards you'll hear them refer to it as a black panel. And this is a steel panel that's painted black and can easily conduct its heat away to whatever it's attached to, which is normally a specimen holder or tray itself. The other type of construction is called an insulated black panel, or sometimes people refer to that as a black standard temperature sensor. And in this case, it's a black steel panel, but it's mounted on a plastic substrate, so it's insulated from conducting that heat away. And as you would expect, the IBP is generally going to be hotter than the black panel. So we talked a lot about this in the temperature section, but in order to maximize acceleration, we really want to use the maximum surface temperature when we're designing a xenon arc test. But to minimize error, we don't want to exceed the surface temperature. We don't want to subject these materials to unrealistic conditions because that can have a huge impact on the correlation of the test to outdoors. Chamber air temperature control is required in certain test methods and primarily used in test methods that require relative humidity, because relative humidity depends on chamber air temperature in order to actually establish how much moisture is in the chamber. To measure chamber air, you have to shield the sensor from light, and in all cases, the black panel should be a higher temperature than the chamber air. If it's not, something is malfunctioning. Relative humidity control is required in some test methods. Textiles use it because a lot of them are not subjected to direct spray, but automotive test methods tend to use it just to reduce variability in tests run in different locations. Xenon arc testers can generate it different ways. Boilers or steam generators, nebulizers, atomizing spray, those are all ways that people will create relative humidity in chambers. But for most durable materials, particularly if you have spray or condensation in the test, relative humidity isn't really important. Xenon arc chambers are also capable of spraying water on specimens. Most test methods specify a front spray if they have any spray at all. Recently, ASTM D7869 developed a method for calibrating and verifying how much water is being delivered to your specimens, which is important. As we mentioned before, this is the one that this is the standard that was developed as part of us identifying that moisture was a huge impact on coatings and that we were downplaying how wet things were outdoors. There's also the capability of backspray, which is used in some automotive tests. This is more a historic point because the original tester wanted to spray on the back of the specimens to create condensation, which doesn't really work in a xenon arc chamber, but all the time they were spraying on the back and the front. And so now the one standard that requires this sprays on the front and the back at the same time. Dual spray is used in some standards to simulate a different solution. This is primarily used to simulate acid rain, or in the case of cosmetics, you can have like a soap solution or a hydrogen peroxide solution. And then the last way is immersion. So this is where you actually submerge a material underwater and expose it to light at the same time. Some standards, any materials that would be installed in like a horizontal manner or anywhere that you would expect to have, significant pooling of water, such as, sealants in roads or roofing, like flat roofing applications, immersion can be useful. So to go over xenon arc altogether, it really is the best simulation of full spectrum sunlight if you're looking for that in an accelerated test. But the lamps do experience aging, which can change the spectrum over time, so it can create some variability there. It does have precise control of temperature effects, and it does simulate the effects of the color of the specimen versus a real-world condition, which is important. A black specimen and a white specimen in a xenon arc will experience that 15 to 25 degree difference. You have the ability to water spray and control, but it is kind of higher cost compared to the next architecture that we're going to be talking about. QLab does offer 3 different types of xenon arc testers. The XE1, which is kind of an entry-level benchtop tester, does not have relative humidity control, but we do have an immersion option for that, so that's used in various industries. The XE2 and XE3 have front and back spray, water spray, relative humidity control. The difference there is that the XE2 is a rotating drum architecture and the XE3 is a flat array. Now we're going to move on to fluorescent UV laboratory weathering. So this is kind of a general schematic of what it looks like. So we have lamps in the center of this chamber that has a heated water underneath it, and the specimens are actually installed on the left and right side of the chamber in this diagram. And that's important for some of the functions that exist in this tester, which we'll talk about here in a bit. So here's what a fluorescent UV lamp looks like, just like the ones that have been installed in offices for a while. But these ones are specially made so that they have spectrums that simulate the UV portion of sunlight. So there are 4 types of lamps that are used. The first one is a UVA 340, which means that its peak is centered around 340 nanometers. And that is designed to simulate daylight, direct exposure, noon summer sunlight. And UVA 351 is designed with a peak at about 351 nanometers, which simulates sunlight behind window glass. The UVB 313 and the QFS 40 are designed to give you shortwave UV that's not realistic, but allows for a faster test on durable materials. And then the last one is cool white to simulate office environments. So here's some of the spectrums. So for UVA 340, as you can see, up until about 360, 370 nanometers, it's a very close fit to sunlight. The UVA 351, same thing when we compare it to sunlight behind window glass. And then when we look at the 313s, you can see that they don't necessarily simulate sunlight at all, but they are good for quality control tests. So in the QUV, we're also capable of controlling the irradiance. It's a similar mechanism as we discussed in the xenon arc, where we're measuring the UV at a sensor, which feeds back to the controller to tell it whether or not to adjust power. Whoa. So one of the advantages of fluorescent lamps is that because they're really focused in the UV range, we can get much higher irradiance than you can get with like a xenon arc. So sometimes you can get faster results if your material is responsive to higher radiance. The irradiance control is a bit easier because the spectrum is stable. Unlike the xenon arc lamps, the only thing that changes over time is the maximum irradiance that can be achieved by a lamp, but the spectrum itself stays the same. And because of that, they're lower maintenance, they're lower price and operating costs, and they're very easy to maintain. One of the downsides of using a fluorescent UV chamber is that because there's almost no visible or IR component, the effects of those on specimen temperature, particularly in regards to their color, is not really present. So as you can see in a UV fluorescent chamber, the difference between a black and white specimen is very small relative to what is actually experienced outdoors. So keep that in mind if you're designing a test with the fluorescent UV, that you know the actual operating environment. The big benefit of using a fluorescent UV, other than the fact that it is less expensive and that the UV is stable is that we can actually generate condensation. As mentioned before, condensation is the most common form of wetness outdoors, and really provides a lot of oxygen to the material. And in this case, it actually allows us to have hot air there. So the way this works is that we have heated water that fills the chamber up with hot, moist air. And because there's room cooling on the backs of the specimens, it cools the front of the specimen enough that in that local area, it drops to, or it gets to 100% relative humidity, and water begins condensing on the surface of the specimens. So the benefit we have there is not only are you getting the realistic wetness, and can you get that for a long time, but it's high temperature. And high temperature means there's more moisture there, and it helps facilitate that chemical reaction. Whereas water spray, you're almost always subject to whatever the temperature of the water coming out is. So, as mentioned, it is the closest match to natural wetness, very high O2 content, and it is the best way to accelerate water in laboratory tester. But what's an also very important thing when it comes to the cost of running a test is if you're not running with water spray, the tester performs the distilling itself, so you don't need to use highly purified water. As long as you have clean tap water and a neutral pH, you can run this test. But for some applications, it is important to still have water spray because that adds more saturation to the part and also gives us a good way to perform that thermal shock that we talked about. Water spray is a little bit more difficult in the QUV. It's a very high rate of water, but most tests do not require water spray. So kind of going back over the fluorescent UV summary, 340 is the best simulation of shortwave UV there is. UVB 313 can be really fast, and both of them have very stable spectrum, which means that your tests are going to be repeatable. There is no visible light, which can be a detriment for some tests, but it does have condensation, which is the most realistic and rigorous moisture test that we have. But there is no RH control, but in most cases, since we have condensation or spray, it's not really necessary. And the fluorescent UV tester that we offer is the QUV, which was the first one brought onto the market. So kind of comparing these technologies, we're going to start talking about what you want to use. But something to keep in mind is that, fluorescent UV is lower cost, inexpensive, and easier to use, but it doesn't simulate full spectrum sunlight. Xenon Arc has that full spectrum. It's a little bit harder to use, a little bit more expensive. Can't do condensation. So you kind of have to balance what your application is and which you think will be more useful. They are complementary technologies. A lot of people will use both. A lot of people will use a Xenon Arc tester for some of the R&D development, finding out what part of the spectrum it's sensitive to, meeting qualifications. But the bulk of their, quality control and all that is done with fluorescent UV testers. So putting this all together, let's talk about elements of an effective testing program. So the first thing you need to do is identify what kind of test you should run. And if you haven't done any weathering testing, let's just cross that bottom one off because you're not going to be there yet. But if you're just looking for a quality control test, that you're going to be looking for different things than if you're looking for some R&D development or correlative testing. So pick which test that you want to run, which type of test, and then find out whether or not you need outdoor data. And if you don't have outdoor data, start collecting that outdoor data as soon as possible. Testing at benchmark sites is not expensive. A lot of people are often, concerned about that, but depending on the size of your specimens and the rate of the test, you could be talking about less than $10 per year per specimen. So keep that in mind. Identify the service environment is your material going to be installed indoors or outdoors? Are your problem places wet or dry climates, hot or cold? These are things to keep in mind when developing an accelerated test. Use best practices. So if you have a failure mode that you're looking for, keep running the test until you get there. If you stop a test prematurely because it met the 2,000 hours that you wanted it to last, you don't know if that material is going to fail at 2,001 hours or 9,000 hours. So run until you actually get to your failure mode. Use multiple replicates. you can run into problems during evaluations, particularly outdoor exposures. If you only have one replicate of a formula and something happens, your data is lost. So you want to make sure that you maintain that data. And also perform evaluations frequently, which is the opposite end of running towards a defined failure mode. If you only run to 2,000 hours and you find out that your material failed, you don't know if that material failed at 10 hours or 1,900 hours. And the final one there is reposition frequently. In order to reduce variability in a tester, we usually suggest repositioning a minimum of 4 to 5 times over the duration of a test. And then now that you know everything that you're looking at, make sure that you pick an appropriate test architecture. If you're running to a standard, it'll tell you which architecture to use. Do you know if full spectrum is important? If it's not, maybe a fluorescent UV is appropriate. How important is water uptake? Do you need that condensation test? Maybe the fluorescent UV is better than a xenon arc. So these are all questions to keep in mind as far as developing your weathering test program. All right, that is it for the portion of the webinar where we went through the presentation. But I think it is important that we're going to stick around for a while. We're going to answer some questions. If you guys have any questions, please use the GoToWebinar ability to submit them. If it's a good question, we'll probably answer it vocally. If it's something that's kind of focused on your application, we will handle it through the questions feature. If you think of a question after the webinar is over and you want to ask it, feel free to email that to info@q-lab.com. And also, as a reminder, we will be sending the slides and video out for this presentation to all attendees. So that should be going out probably tomorrow. And so if you don't receive it by next week, then feel free to contact us.
One question that came in, Bill, so far is you were talking about the 340 versus the 420 nanometer cutoff for that. Why is 420 nanometers considered a better control point for indoor compared to 340?
The reason they use 420 nanometers is part of having good control is you want to make sure that you have significant intensity to get kind of precision control. So ironically, usually when we're concerned about the cut-on daylight of 295 nanometers, we control at 340 because the actual irradiance at 295 is very low. And so it would be hard to actually control the tester there. So the same thing kind of applies behind window glass. While the cut-on is between 310 and 330 nanometers, you don't really get enough of an irradiance to really get precise control until you go out a little bit more.
Another question came in that says, it seems like xenon arc is the best option for outdoor exposures. However, if UV-only exposure is done, do the correlations generally hold?
It depends on the material. Some materials. So the key there is that there are some materials that are sensitive to long wave and visible light as far as photodegradation goes. And for those materials, you're not going to find a better solution than xenon arc for matching outdoors. But there's plenty of data, anecdotal data based on other people's collection that there are test methods where we found that fluorescent UV has very close to similar correlation to outdoor as xenon arc. One example of that is there was a study that was done on various exposures in fluorescent UV and xenon arc to simulate 6-month outdoor exposure of flexible intermediate bulk containers, so FIBCs. And I don't have the data in front of me, but I believe with a UVA 340 QUV test and with a xenon arc test, the difference in correlation between them was negligible. I want to say it was 0.85 rank order to 0.87, which is both very good and very close, if you don't know what those numbers mean. So in that case, maybe a fluorescent UV would be fine. But if you're not sure, if you're unsure about the sensitivity of your material to long wave UV or visible, xenon arc is going to be the best choice. Oh, and if your material's very susceptible to condensation or moisture ingress, then, in some of those cases, you might actually get better correlation from the QUV. In particular, there's a lot of Xenon Arc tests out there. Most of the ones with water spray, the water spray is deficient. So what it's doing there is it's washing off specimens, and it's causing thermal shock, but it's not actually causing any water uptake. So comparing one of those test cycles to a fluorescent UV test cycle with condensation, you might get better correlation with a fluorescent UV.
All right, just a reminder, if you have questions, we're here a couple more minutes. If you want to use the question box in the GoToWebinar control panel, we are here answering them for a couple more minutes, so we'll watch for some more questions.
Question that said that a lot of test labs are reluctant to kind of suggest a test method to run, and part of the reason behind that is that and this is something that's very close to us at QLab. We are experts in weathering, but we're not experts in your material. And the problem is that different materials react differently to different tests. So we might get good correlation with a fluorescent UV 313 lamp. Even though that's not a realistic UV, and we have no way of testing that. We don't know what materials are sensitive to. We don't know the impact of water uptake on those materials. So I think that test labs run into that same problem. Is they're experts in running tests. They're not necessarily experts in how your particular formula of coating or plastic or any of that is going to actually perform. And so it's tough for us to know enough about your part to really suggest a test method.
Can you talk a little bit more about the difference between the UVA 340 bulb and the UVB FS40?
So you mean the UVA and the UVB, or the? All right. So there are three lamps there. We'll cover all of them. The UVA 340 is designed to match noon summer sunlight. So the UVs that you see that delivers are realistic. So if you're looking for a realistic test, the UVA 340 is probably the best. The UVB 313 and the FS40 are designed to give you short wave with a cut-on of about 280 nanometers. So it's not realistic, but in general, the shorter the wavelength, in most times, the harsher the exposure. And so it can give you a faster test, but it's less likely to correlate to outdoor exposures. Now, we had both the UVB 313 and the FS40. The only difference between those lamps is the maximum irradiance. So the UVB 313 EL, which is what we suggest for any irradiance-controlled device, allows for higher UV exposures with the same spectrum as the FS40.
All right, this one gets really in the weeds. And again, they're asking, how does the moisture in the QFOG corrosion chamber compare to the condensation effects of a QUV?
They're somewhat, they're similar but different. So there's a standard in ISO called ISO 6270, which is designed for exposing materials to an aqueous environment. 6270-1 is continuous condensation, which it would be something that you'd see in like the QUV. ISO 6270-2 is exposure to 100% relative humidity environment. and that would be the kind of thing that you'd see in like a QFog. So they're similar in what they're trying to do, but I think the actual overall effect is that you'll see a lot more moisture uptake in a QUV than you'll see in a QFog.
This is the last call for questions. And again, if you think of something after the fact, you can email us. It's info@q-lab.com. And also stay tuned for some of our future webinars. We will put those on our Twitter account as well as our website at q-lab.com, and watch your email boxes for those announcements as well. So we'll leave it open for one more moment here for any final questions before we wrap up the webinar. With no more questions, we're going to end this webinar. Thank you for joining us today for this QLab webinar, and stay tuned for future webinars. Thanks very much.
Thanks for attending.